The story of why light has a speed limit does not begin in the vacuum of space or in the hushed halls of modern laboratories, but in a world lit only by fire, where ancient astronomers lifted their eyes toward the night sky and tried to decipher the silent messages scattered across the darkness. Imagine the first priests of Babylon stepping onto stone terraces still warm from the day's sun, drawing lines in the sand to mark the wandering paths of the stars, never suspecting that every glimmer above them was already old by the time it touched their eyes. They recorded positions, traced patterns, predicted omens, yet not one of them considered that the light they were reading might be traveling, that it might have a velocity of its own, that its motion might hold the blueprint for the very architecture of the universe. In those early centuries, light was simply presence, instant, divine, impossible to grasp, and the question of whether it had a speed would have seemed as pointless as asking whether a god walked or flew. It would take centuries before anyone dared to wonder whether illumination might be delayed by distance. And even then, the idea felt almost blasphemous, as if suggesting that the universe hesitates before revealing itself. Across the Mediterranean, Greek philosophers debated the nature of perception with the same fervor as generals planning a campaign. Empedocles claimed that light must have speed because it travels, moving from one object to another. Aristotle dismissed this notion entirely, insisting that light was a mere quality of the transparent, manifesting instantly, without motion. The argument drifted through the Lyceum's open colonnades and over manuscripts copied by generations of scholars, becoming part of a philosophical tradition that shaped medieval thinking for more than 1,000 years. And yet, buried within Empedocles' abandoned idea was a seed, the possibility that the cosmos contained an invisible timescale, a delay so small that no naked human sense could detect it. When Islamic astronomers inherited the mantle of ancient Greek inquiry, they preserved Aristotle's influence, but also began pressing at its boundaries. The polymath Alhazen, working in the 10th century in the Fatimid city of Cairo, dissected light with an experimental rigor unheard of in antiquity. He studied reflection and refraction, filled dark rooms with carefully carved apertures, tracked the journey of rays across air and water, and established that vision depended on light entering the eye rather than emanating from it. Yet even he, so meticulous in experiment, considered the speed of light to be either instantaneous or simply too fast to measure. It was a practical concession in an age before clocks accurate enough to catch a beam of light in motion. But the very act of wondering how light behaved inside different media planted a quiet doubt in the old Aristotelian certainty. By the 17th century, Europe was alive with new instruments, new mathematics, and a spirit of rebellion against inherited authority. Galileo Galilei, restless, sharp-eyed, and impatient with philosophical abstractions, decided to test the question with the most direct experiment he could imagine. On one moonlit evening near Florence, he stationed 2 assistants with shuttered lanterns on distant hilltops. One would open his lantern, the other, upon seeing the flash, would open his own, and the difference in timing, if any existed, would reveal the speed of light. But the distances were too short, the lanterns too dim, and human reaction times far too slow. The experiment yielded nothing but frustration, yet Galileo's willingness to challenge Aristotle with measurement rather than argument marked a turning point. He had cracked the seal on a question that would soon draw the attention of Europe's greatest minds. Not long after, the universe itself provided a better clock than anything Galileo could build. In the 1670s, the Danish astronomer Ole Romer stationed himself in Paris, observing the eclipses of Io, one of Jupiter's moons. He noticed something peculiar. When Earth moved closer to Jupiter, Io's eclipses appeared ahead of schedule. When Earth moved away, the eclipses lagged. Romer realized that the delay came from light having to travel farther as Earth drifted along its orbit. With nothing but a telescope, careful notes, and fierce patience, he became the first person in history to extract a finite value for the speed of light, as if he had reached across space and taken a measurement from the universe's own clockwork. The number was rough but revolutionary, breaking a millennium-long assumption that light was instantaneous. For the first time, humanity glimpsed that illumination was not the universal exception to motion. It obeyed laws, possessed velocity, and therefore might hold within it deeper secrets about nature. The 18th century refined Romer's discovery with increasing precision, driven by the work of James Bradley, whose search for stellar parallax led to the unexpected detection of stellar aberration, a tilt in the apparent position of stars caused by Earth's orbital motion combined with the finite speed of incoming starlight. Bradley's measurements trimmed the estimate of light speed with a surgeon's delicacy, and suddenly, scientists understood that light's velocity was not merely a curiosity, but a fundamental cosmic parameter woven into observations of the heavens. Every star's twinkle arrived from the past. Every nebula's glow was a message delayed by a calculable span of time. Every sunrise carried within it the imprint of the 8 minutes it took for the sun to reach Earth. Light had become a traveler, and the sky transformed from a static dome into a dynamic stage where the speed of illumination governed what could be seen and when.
Yet it was in the 19th century, amid the rise of electromagnetism, that light's speed began to speak with profound authority. Michael Faraday, the self-educated son of a blacksmith, brought to the study of electricity and magnetism an imagination shaped not by algebra, but by lines of force he envisioned stretching through space like threads pulled taut by invisible hands. His experiments revealed that electric and magnetic fields were not isolated phenomena, but danced around each other, each capable of inducing the other to change and propagate. Then came James Clerk Maxwell, who translated Faraday's intuitive sketches into mathematics of astonishing clarity. In the heart of Maxwell's equations lay a prediction. Disturbances in electric and magnetic fields would ripple through space at a specific speed, and that speed matched the measured speed of light. Suddenly, light was no longer a mysterious, ethereal substance. It was an electromagnetic wave, born from the interplay of fields that pulsed through the vacuum of space. And with that realization came another. The speed of light was not an accident, but a fundamental property of the vacuum itself, set by the electric permittivity and magnetic permeability that defined the structure of empty space. Scientists of the era began to suspect that if light's speed was tied to the electromagnetic properties of space, perhaps it was also tied to a deeper medium, a mysterious substance that filled the universe and carried waves the way air carries sound. This hypothetical substance was the luminiferous ether, and for decades it dominated scientific thought. Laboratories across Europe filled with increasingly elaborate contraptions designed to detect the Earth's motion through the ether. The most famous of these was the Michelson-Morley interferometer, a delicate instrument capable of comparing the speed of light along different directions of Earth's presumed motion. When Michelson and Morley executed their experiment in 1887, they expected to detect shifts in interference patterns as light beams moving upstream or downstream through the ether changed speed. But the result was null. No shift, no difference, no trace of ether. Light's speed appeared to be the same in every direction, as though the universe had no preferred rest frame at all. This null result lingered as a scientific irritant, a puzzle that refused to conform to expectations. Some physicists proposed that objects physically contracted in the direction of motion through the ether, compensating for the expected shift. Others offered mathematical patches that explained the data without challenging ether's existence. But beneath these increasingly tangled explanations, a deeper truth was waiting, one that required a new way of thinking about space, time, and motion altogether. And into this intellectual landscape stepped a young patent clerk named Albert Einstein, whose mind was unencumbered by academic orthodoxy, and whose intuition about the nature of symmetry and simplicity was as sharp as any in the history of science.
Einstein's breakthrough in 1905 was not a sudden revelation, but the culmination of years spent imagining what it would be like to chase a beam of light, an exercise he began as a teenager. He realized that if Maxwell's equations predicted a constant speed of light regardless of the observer's motion, then perhaps it was not the equations that needed adjusting, but the very notions of space and time themselves. Instead of assuming a universal clock and an absolute grid of positions, he allowed time to flow differently for different observers and lengths to contract depending on motion. Out of this audacity came the theory of special relativity, a framework in which the speed of light emerged as the maximum speed at which information, energy, or causality could propagate, not because light was privileged, but because space-time itself imposed that limit. Einstein's reimagining of space and time did not simply declare light speed to be constant. It revealed that the universe was constructed in such a way that any attempt to exceed that speed would twist the geometry of reality into impossibility. Time slowed as velocity increased, lengths contracted in the direction of travel, and the very notion of simultaneity fractured into observer-dependent slices of experience. In this new landscape, the speed of light was akin to the horizon on the open sea. No matter how one sailed toward it, it remained always ahead, shaping the range of all possible journeys. The fact that massless particles like photons moved at this cosmic speed was not a clue of their specialness, but a testament to their freedom from the inertia of mass, allowing them to glide along the natural contours of space-time without consuming energy to accelerate. Meanwhile, anything with mass found itself bound by the energy requirements that soared toward infinity as it neared light's pace, trapping massive objects below the universal limit as surely as gravity binds planets to their orbits. But the narrative does not remain in the quiet room of Einstein's burned patent office. It surges outward into the laboratories of the early 20th century, where physicists raced to test the predictions of relativity with increasingly sophisticated tools. Astronomers tracked starlight grazing the edge of the sun during a total solar eclipse, confirming the bending of light predicted by general relativity. Particle physicists watched high-speed muons, born in the upper atmosphere by cosmic rays, survive far longer than classical physics allowed, because time flowed differently for them as they approached the cosmic limit. These observational triumphs transformed relativity from a radical idea into a pillar of scientific understanding, and with each victory, the speed of light became less of a mere numerical constant and more of a boundary encoded into the fabric of reality. Yet, even as relativity illuminated the upper limits of speed, new mysteries emerged from the quantum world that seemed to challenge the very notion of locality. In the 1920s and 1930s, the quantum revolution revealed that particles could behave as waves, occupy superpositions, and become entangled in ways that suggested instantaneous correlations across distance. Einstein, Podolsky, and Rosen famously proposed a thought experiment to illustrate what they saw as the incompleteness of quantum mechanics, suggesting that if the theory were correct, entangled particles could influence each other faster than light, violating the speed limit imposed by relativity. For Einstein, this spooky action at a distance was an affront to the principle that information could not travel faster than the cosmic constant. For his contemporaries, it was a puzzling but unavoidable consequence of the new quantum formalism. As decades passed, experiments by physicists such as John Bell, Elaine Aspect, and countless others confirmed the predictions of quantum entanglement with increasing precision. Yet none of these experiments succeeded in transmitting usable information faster than light. The correlations were real, instantaneous, and profound, but they did not permit communication or causation across the gap. The speed limit remained intact, revealing the subtle distinction between entanglement's echo-like intimacy and the transmission of information across space. While two entangled particles could behave as if they shared a hidden unity, any attempt to exploit this unity to send a signal ran headlong into the statistical nature of quantum measurements, which ensured that faster-than-light communication remained forbidden. The universe, it seemed, could weave together events in ways stranger than even Einstein imagined, yet it still guarded the boundaries of causality with unwavering strictness. Meanwhile, the realm of high-energy physics brought its own confrontations with the cosmic speed limit. As particle accelerators grew in scale, from the early cyclotrons of Ernest Lawrence to the massive synchrotrons and colliders of the mid-20th century, physicists observed particles being pushed closer and closer to the speed of light. No matter how much energy they poured into electrons or protons racing around circular tracks, the particles' velocities increased only imperceptibly, while their masses effectively ballooned, demanding exponentially more energy for smaller and smaller gains in speed. Researchers saw Einstein's equations play out in the sparks and trajectories of particle beams, not as abstract principles, but as the tangible, measurable behavior of matter. The closer a particle approached the cosmic limit, the more it behaved like a traveler climbing a mountain that grew steeper with every step, until the summit became effectively unreachable.
Yet these same accelerators revealed another, more subtle truth. Objects could, and did, exceed the speed of light in mediums other than a vacuum, producing the eerie blue glow of Cherenkov radiation as they outran the phase velocity of light in water or glass. This phenomenon delighted physicists, not because it violated Einstein, it did not, but because it showed how the cosmic speed limit was tied not to an everyday measurement of light's velocity in matter, but to the deeper, invariant structure of space-time itself. In vacuum, nothing material could surpass light's speed. In other media, the reduced effective speed of light permitted these brief, ghostly sprints that illuminated nuclear reactors and gave researchers another window into the strange interplay between matter, energy, and the electromagnetic field. As the 20th century progressed, the speed of light became enmeshed not only in theoretical physics, but in the practical technologies of daily life. The global positioning system, for instance, relied on satellites orbiting high above Earth, their clocks ticking at different rates due to both special and general relativity. Engineers designing GPS receivers had to account for the finite speed of light when interpreting signals from multiple satellites to determine a precise location on the ground. Without relativistic corrections, tiny adjustments rooted in the same principles that declared light's speed absolute, every GPS coordinate would drift by kilometers each day. Thus, travelers navigating city streets with handheld devices unwittingly depended on the cosmic speed limit discovered by Romer, refined by Maxwell, confirmed by Michelson and Morley and illuminated by Einstein. But the narrative continues deeper still, stretching toward the edge of modern cosmology, where light speed shapes the very structure of space-time. In the expanding universe described by general relativity, distant galaxies recede from us not because they are moving through space at extraordinary speeds, but because space itself is stretching. This cosmic expansion leads to apparent velocities exceeding the speed of light at great distances, an occurrence permitted because the recession is not a motion through space, but an expansion of space. Astronomers observing galaxies billions of light years away see them moving away faster than light, yet this does not violate relativity. Instead, it transforms the meaning of distance and motion on cosmic scales, revealing that light's speed limit governs local interactions, while the broader evolution of the universe obeys its own geometric dynamics. Still, the cosmic speed limit retained its sovereignty in every local experiment, every particle collision, every transmission of information. And theoretical physicists, probing the early universe and the boundaries of black holes, discovered that light's role was even stranger near the most extreme gravitational environments. Near a black hole's event horizon, the warping of space-time was so intense that light attempting to escape from the surface appeared to slow, redshift, and ultimately freeze at the boundary from an outside observer's perspective. The speed of light did not change. Instead, space-time itself bent and stretched until escape became impossible. The event horizon became a one-way wall, not because light lost its velocity, but because the geometry of space-time funneled all possible trajectories inward.
As physicists traced the edges of these gravitational abysses, they realized that the speed limit of light was intricately bound to the way space-time encoded information. The event horizon of a black hole was not merely a point of no return for matter and light. It was a boundary where the conventional notions of time, space, and causality bent into unfamiliar shapes. Signals could not escape from within, not because their speeds faltered, but because every possible path through space-time curved back inward, like a maze whose every corridor led deeper into darkness. Light's unwavering pace was transformed by the warping of space-time into a desperate struggle against a landscape tilted so steeply that escape became impossible. In the equations of general relativity, the speed of light remained constant, yet the geometry surrounding it dictated which directions were reachable, which were forbidden, and which became trapped forever behind the horizon. As the study of black holes matured, theorists such as John Wheeler and Roger Penrose pushed further into the realm where quantum mechanics and relativity collided. They discovered that the speed of light's constancy shaped not only how black holes captured light, but also how they encoded information about their contents. Penrose diagrams revealed how space-time could be compressed and reshaped to display the causal structure of cosmic events, with diagonal lines representing light's immutable path and vertical and horizontal regions representing the possible futures and pasts accessible to massive objects. In these diagrams, light became the skeleton upon which the entire causal framework of the universe was built. every future event, every past cause, every potential influence was bound within a light cone, an expanding boundary that defined what could possibly interact and what lay forever beyond communication. This realization rippled into the emergence of quantum field theory, where fields, rather than particles, were considered the fundamental entities of nature. In the vacuum, fields fluctuated with energies and uncertainties, birthing and annihilating virtual particles too fleeting to observe directly, yet crucial to the structure of the cosmos. Even in this quantum dance, the speed of light imposed strict limits. No virtual excitation could transmit information faster than light. No disturbance could outrun the propagation speed dictated by the field's equations. The vacuum, far from being empty, buzzed with activity. Yet all of this activity respected the same cosmic boundary, weaving the tapestry of quantum interactions within a frame shaped by the speed limit discovered centuries earlier. The 20th century's second half brought a new level of precision, as scientists developed laser interferometers capable of measuring distances smaller than the diameter of a proton. With these tools, they investigated how light behaved over vast distances and in extreme conditions, seeking tiny deviations that might hint at cracks in the speed limit's foundation. Yet each experiment reaffirmed the same conclusion. The speed of light in vacuum remained constant, unperturbed by motion, gravity, or orientation. Even as researchers probed for hypothetical particles, such as tachyons, theoretical entities that, if they existed, would always travel faster than light, no evidence surfaced to challenge the cosmic boundary. Tachyons, interesting as mathematical possibilities, remained exiled from reality, their existence incompatible with the stability and causality of the universe as observed.
At the same time, the frontier of cosmology expanded further, exploring the infancy of the universe in the first fractions of a second after the Big Bang. During this primordial epoch, space expanded at an extraordinary rate in a process called inflation, stretching quantum fluctuations into cosmic structures that would eventually form galaxies and clusters. Although inflation expanded space faster than light, the rule of relativity remained unbroken because no object traveled through space faster than the cosmic limit. Rather, space itself expanded, carrying objects along like leaves on a swiftly widening river. This distinction between motion within space and the expansion of space was subtle but crucial, revealing how the speed of light shaped not only the motion of particles, but the evolution of the cosmos on its grandest scales. While cosmologists wrestled with the early universe, another revolution was taking shape in the study of information and computation. The speed of light became a practical constraint on how quickly information could be transmitted across circuits and networks. In supercomputers, the greatest delays often arose not from the processing time of transistors, but from the finite speed at which signals traveled between components. Engineers designing faster machines confronted a paradox. The greater the computational power, the more significant the physical distances inside the machine became. Wires only a few centimeters long introduced delays measurable in nanoseconds, and as processors shrank and clock speeds rose, even the speed of light became a bottleneck. This tension drove innovations in chip architecture, parallel processing, and optical communication, embedding the speed limit into the technological infrastructure of the digital age. Meanwhile, in the realm of information science, researchers explored how entanglement and quantum teleportation might allow new forms of communication or computation. Yet even here, where quantum states could be transferred between particles separated by vast distances, the process respected the constraints of relativity. Quantum teleportation did not transmit particles themselves faster than light, nor did it allow information to bypass the cosmic speed limit. Instead, it relied on the transfer of classical information transmitted at or below light speed to complete the process. Thus, even the most exotic feats of quantum engineering remain tethered to the same boundary, affirming the deep harmony between the quantum world and the relativistic fabric of spacetime. At the cutting edge of theoretical physics, researchers attempted to reconcile general relativity with quantum mechanics, seeking a unified framework that would explain both gravity and the behavior of subatomic particles. In string theory, where particles were seen as vibrating one-dimensional entities, the speed of light emerged naturally as a fundamental parameter dictating how strings oscillated and interacted. In loop quantum gravity, spacetime itself was quantized into discrete units, yet the propagation of light remained bounded by the same cosmic speed. Even in the most speculative theories about extra dimensions, branes, and multiverses, the universality of light's speed appeared as a guiding principle, an anchor that anchored the laws of physics across countless hypothetical structures. And still the investigation continued, extending into the behavior of spacetime at the Planck scale. Distances so small and energies so high that quantum fluctuations could tear the fabric of reality into foamy, turbulent structures. Some physicists proposed that at such scales, the speed of light might vary slightly, offering a potential explanation for certain cosmological phenomena. Others argued that any variation would disrupt the stability of physical laws and was therefore forbidden. Experiments using gamma-ray bursts, colossal explosions at the edges of the observable universe, sought tiny delays in high-energy photons that might indicate a breakdown of Lorentz invariance. Yet, even across billions of light-years, no such deviations appeared conclusively, and light's constancy remained one of the most resilient features of modern physics. The narrative, however, takes another turn as physicists explore the interior of stars, the behavior of plasmas, and the structures of neutron stars and magnetars. In these extreme environments, light interacts with matter so dense that it takes thousands of years to escape from a star's core, inching its way outward in a diffusive process that belies its incredible vacuum speed. In the heart of the sun, a photon can spend millennia bouncing among nuclei before finally reaching the surface and racing to Earth in 8 minutes. The speed of light remains unchanged, yet the environment impedes its journey, revealing how matter and radiation weave together to create the energy balance sustaining stellar furnaces across the cosmos. Deep within neutron stars, where atoms are crushed into degenerate seas of neutrons, and where magnetic fields spiral with intensities unimaginable on Earth, the passage of light becomes even stranger. Photons interacting with such magnetic strengths can split, merge, or convert into exotic particles. Yet even in these surreal conditions, the fundamental speed at which light propagates in vacuum remains unchanged, like a silent metronome beating beneath the chaos. In these stellar realms, physicists gained insight into how the interplay between extreme density and electromagnetic fields influences radiation, not by altering its cosmic limit, but by sculpting the paths available for it to follow. Every beam, no matter how battered or delayed by the medium, carried the imprint of the unyielding boundary that underpinned all its interactions, reminding researchers that even the universe's most violent laboratories obeyed the same inviolate rules. On Earth, laboratories reproduced slivers of these extreme environments, using high-powered lasers to probe the structure of plasma in fusion reactors, and heavy ion collisions to mimic the early moments of the Big Bang. In these experiments, scientists generated quark-gluon plasma, a near-perfect fluid in which quarks and gluons roamed freely, liberated from the confines of protons and neutrons. Even in this primeval soup, where temperatures exceeded trillions of degrees and matter approached its most fundamental form, the speed at which disturbances rippled through the medium remained capped by the same constant that governed light in vacuum. The cosmic limit reasserted itself in every attempt to push matter and energy to their extremes, shaping not only the behavior of particles, but the fundamental symmetries that defined the universe's earliest instants.
Amid these high-energy pursuits, the philosophical implications of light's speed limit continued to unfold. The idea that causality, the ordering of events into cause and effect, depended entirely on this limit, led scientists and philosophers to reconsider what information truly meant. The light cone, once a mathematical abstraction,
became a conceptual boundary dividing the reachable from the unreachable, the knowable from the forever sealed. Events lying outside one's light cone were not merely distant, they were causally disconnected, incapable of influencing or being influenced by anything within. This causal structure gave the universe its coherence, preventing paradoxes that would arise if signals could travel arbitrarily fast. Light's speed, thus, became the arbiter of temporal order, ensuring that the forward flow of time remained consistent for all observers, even when their perceptions of duration and simultaneity diverged. This causal structure manifested in unexpected ways as researchers investigated the quantum vacuum more deeply. Vacuum polarization, the temporary formation of particle-antiparticle pairs that flickered into existence and vanished almost instantly, subtly influenced the propagation of photons, especially in regions with strong electromagnetic fields. Yet even this quantum jitter could not grant photons a route beyond the universal speed limit. Instead, it introduced minute corrections to their effective speed in specific environments, adjustments so slight that only the most sensitive experiments could detect them. The speed of light in vacuum remained untouched, while the interplay between light and matter added nuance to the behavior of electromagnetic waves under different conditions. The cosmic boundary held, even as quantum field theory revealed a vacuum teeming with dynamic structures and interactions. As physicists probed the limits of relativity, hypothetical constructs emerged: wormholes, warp drives, and shortcuts through space-time that, at least mathematically, appeared to circumvent the cosmic speed limit. These ideas captured imaginations, both scientific and popular, drawing on the possibility that space-time's geometry might permit faster-than-light travel, not by accelerating an object, but by altering the structure of space itself. Solutions to Einstein's equations hinted at tunnels connecting distant points, or bubbles of space-time expanding behind and contracting ahead of a craft, effectively granting superlunar travel without violating the local speed of light. However, each of these solutions required exotic matter, forms of energy with negative density or pressure that had never been observed, and that might be fundamentally incompatible with the stability of the universe. Physicists continued to explore these ideas not because they expected practical devices to emerge, but because such thought experiments illuminated the boundaries of what relativity allowed and what it forbade.
Simultaneously, the study of the universe on the largest scales revealed profound implications for the speed of light. Observations of distant galaxies showed that the expansion of the universe was not merely continuing, but accelerating, driven by a mysterious force dubbed dark energy. As space expanded faster and faster, more galaxies slipped beyond our cosmic horizon, the boundary beyond which light emitted now would never reach us. This horizon was not a physical barrier, but a manifestation of the interplay between cosmic expansion and the finite speed of light. A galaxy receding faster than light due to the expansion of space was not breaking any rules. Rather, it was moving in a universe where geometry itself defined what could be observed. The cosmic speed limit, coupled with the acceleration of expansion, meant that the observable universe had an ever-shifting boundary, and vast regions of the cosmos would remain forever inaccessible. Even closer to home, the constancy of the speed of light shaped the mysteries of dark matter, the invisible substance outweighing ordinary matter 5-1. Although dark matter did not emit or absorb light, its gravitational influence determined the motion of galaxies and the structure of cosmic filaments. The inability to detect dark matter directly seemed to place it outside the realm of electromagnetic interaction. Yet its existence was inferred through light's behavior. Gravitational lensing, galaxy rotation curves, and the cosmic microwave background all revealed its presence. Light, bending around concentrations of dark matter, became a messenger of the unseen, tracing the contours of invisible structures across billions of light years. In this way, the speed of light, combined with gravity, formed a bridge between the visible and the hidden, allowing cosmologists to map the dark scaffolding of the universe. As researchers explored the cosmic microwave background, the faint afterglow of the Big Bang, they discovered that variations in temperature and polarization across the sky held clues about the universe's earliest moments. The speed of light, together with the rate of cosmic expansion, determined how far sound waves could travel in the primordial plasma, imprinting acoustic peaks in the radiation that satellites such as COBE, WMAP, and Planck later detected with exquisite precision. These observations provided a detailed snapshot of the universe at 380,000 years old, a time when light finally escaped from the charged fog that had dominated since the Big Bang. The structure of these acoustic peaks revealed the universe's composition, geometry, and evolution, turning the speed of light into a cosmic ruler by which the earliest distances and timescales could be measured. In parallel, theoretical developments in black hole thermodynamics brought new insights into the relationship between light, gravity, and information. Stephen Hawking's discovery that black holes could emit radiation due to quantum effects near the event horizon shocked physicists, suggesting that black holes were not eternal prisons, but slowly evaporating entities. This Hawking radiation emerged from the creation of particle-antiparticle pairs, one of which escaped while the other fell inward. Yet even this escape adhered strictly to the speed limit imposed by relativity. The radiation carried energy and information away at a pace dictated by the black hole's mass, revealing a subtle interplay between quantum field theory and the geometry of spacetime. Light's speed limit once again served as the gatekeeper for causal influence, ensuring that even the evaporation of black holes unfolded within the boundaries set by relativity. The study of Hawking radiation
soon intersected with a deeper puzzle, the black hole information paradox, which asked whether information about matter falling into a black hole was truly lost forever, or somehow preserved in the subtle correlations of the emitted radiation. The paradox forced physicists to confront the relationship between quantum mechanics, which demanded that information be conserved, and general relativity, which seemed to bury it behind an event horizon. The resolution of this conflict, still unfolding in the halls of theoretical physics institutes, drew heavily on the nature of light's speed limit. The horizon that trapped light also trapped information, and any mechanism allowing information to escape would need to comply with the causal structure defined by the light cones surrounding the black hole. In holographic theories, which suggested that all information inside a volume could be encoded on its boundary, the speed of light again appeared as a fundamental constraint, shaping how information flowed across this strange, projected surface of reality. As the holographic principle evolved, researchers working on the ADS-CFT correspondence discovered that space-time itself might emerge from the entanglement structure of underlying quantum systems. In this framework, distances, geometries, and even gravitational dynamics were encoded in patterns of quantum correlations, and light's path through space-time reflected the structure of these correlations. The maximum speed at which these correlations could reorganize themselves was tied to the same limit that governed light. In this way, the speed of light became not just a constant of motion, but a manifestation of deeper principles governing how information knitted together the fabric of space-time. Each light-like trajectory revealed how geometry emerged from entanglement, with the cosmic speed limit ensuring consistency between the quantum world and the classical structure it generated. In laboratories around the world, condensed matter physicists began constructing analogs of relativistic systems using materials where electrons behaved like massless particles. In graphene, for instance, charge carriers moved with effective speeds governed by the structure of the lattice, mimicking relativistic dynamics on a tabletop. Although the effective speed of these quasi-particles was far lower than the cosmic constant, the analogous speed limit within the material replicated many features of special relativity, including the impossibility of accelerating carriers beyond that effective light speed. These condensed matter experiments provided new ways to simulate phenomena such as black hole horizons, Hawking radiation, and even aspects of quantum gravity, revealing how the concept of a speed limit could arise naturally from the interplay of microscopic interactions. Elsewhere, metamaterials engineered with precise patterns of refractive indices enabled the creation of optical cloaks, negative refraction, and slow light effects, in which pulses of light appeared to crawl at walking speed. Yet even in these systems, where the group velocity of light could be manipulated dramatically, the underlying laws of electromagnetism insisted that no information or causal influence traveled faster than the vacuum speed of light. The pulse compressions and expansions that created the illusion of superluminal or subluminal propagation always conspired to maintain the integrity of causality. Researchers exploited these effects for practical technologies, advanced imaging, communications, and sensing, but the cosmic limit stood firm beneath every engineered illusion.
The constant reappearance of the speed of light in seemingly unrelated fields, cosmology, quantum information, condensed matter physics, and gravitational theory, hinted that it served as a unifying principle far beyond its original interpretation as the velocity of electromagnetic waves. As ambitious experiments probed for any variation of this constant across cosmic time, using observations of distant quasars and ancient stars, they found no convincing evidence that the speed of light had changed over billions of years. If it had varied in the early universe, the effects would ripple through the structure of galaxies, the abundance of elements, and the fingerprints of the cosmic microwave background. Yet the consistency of these cosmic indicators suggested that the speed limit stood unaltered throughout cosmic history, a steadfast marker of stability amid epochs of expansion, collapse, and evolution. Meanwhile, in the practical realm of interstellar exploration, the speed of light emerged as a barrier shaping humanity's cosmic ambitions. Signals sent to spacecraft at the edge of the solar system took hours to arrive, and images returned from distant probes were snapshots from the past. Visionaries dreaming of voyages to other stars had to confront the reality that even the nearest stellar neighbor lay more than 4 light-years away, a gulf that made relativistic travel an engineering and economic challenge beyond anything yet achieved. But this limitation also sharpened the imagination, inspiring studies of generation ships, cryogenic stasis, and robotic emissaries designed to endure journeys lasting centuries. The cosmic speed limit, once a curiosity of theoretical physics, became a constraint that defined the scope of humanity's future among the stars. At the same time, discussions in the philosophy of physics explored how the speed of light shaped not only scientific understanding, but human perception of reality. The finite travel time of light meant that all observation was inherently historical. Every image of the night sky was a glimpse into the past. Every supernova captured by telescopes a ghostly event long concluded. The observable universe became not a spatial boundary, but a temporal one, its limits defined by how far light had traveled since the Big Bang. This realization transformed the very meaning of observation, revealing that the cosmos visible to us was only a fraction of what existed, bounded not by distance, but by time and the immutable pace of light. In the forefront of quantum gravity research, new ideas emerged suggesting that space-time might be composed of discrete units, each separated by Planck-length intervals, with the speed of light defining the maximum rate at which such units could interact.
Whether framed as a lattice, a spin network, or a dynamic graph, these theories all preserved the speed limit as a key structural feature, suggesting that the universe's most microscopic architecture still respected the same boundaries observed at macroscopic scales. Light, weaving through this quantized texture, preserved the continuity of physical law across an astonishing range of energies and distances, linking the smallest scales with the largest cosmic structures.
As astrophysicists studied the violent mergers of black holes and neutron stars newly detected through the ripples of gravitational waves, they discovered that these waves too traveled at the speed of light. The simultaneous arrival of gravitational waves and electromagnetic signals from distant collisions confirmed that gravity itself propagated at the same speed, a profound result that reinforced the unity of space-time dynamics. This equivalence tied the behavior of gravity, light, and causality together more tightly than ever, revealing that the cosmic speed limit applied not only to particles and fields, but to the very distortions of space-time that carried information across the cosmos. And when gravitational wave detectors such as LIGO and Virgo captured these elusive signals, physicists realized they were listening to the universe with new senses, attuned to vibrations in the cosmic fabric itself. The crisp arrival times of these waves, synchronized across detectors separated by continents, provided yet another confirmation that the speed of gravity matched the speed of light to extraordinary precision. Even the most violent cosmic catastrophes, black hole mergers swallowing entire stars in seconds, adhered to the same universal constraint that shaped everything from photon trajectories to the operation of GPS satellites. As gravitational astronomy matured and observatories tuned themselves to ever fainter murmurs, the universe revealed more of its hidden architecture, and the constancy of light speed continued to anchor each discovery. Every recorded chirp of colliding neutron stars, every subtle tremor of coalescing black holes, every fleeting whisper from a distant supernova spoke the same language, carried across cosmic expanses at the unchanging rate that had shaped the universe since its first incandescent moments. Even when detectors captured signals from billions of light-years away, when space-time itself had stretched the waves into elongated echoes, the underlying propagation speed remained unchanged. The universe transmitted its deepest events through channels bound to the same constraint that governed a photon's flight in a laboratory experiment, tying together the smallest and largest scales of existence with striking coherence. As computational models grew more sophisticated, simulating the evolution of the cosmos from the Big Bang to the present, the speed of light emerged again and again as a crucial parameter. It defined the thickness of the cosmic photosphere, the rate at which ionization fronts spread after the universe's first stars ignited, the patterns traced by cosmic inflation, and the maximum reach of information in the primordial plasma. With every refinement, simulations reaffirmed that the speed limit was not an incidental value, but a foundational one, woven so deeply into the behavior of the universe that altering it would collapse the delicate balance of forces, symmetries, and interactions that permitted structure, chemistry, and life.
In more speculative corners of theoretical physics, researchers explored whether the speed of light might emerge from deeper mathematical constructs, from the geometry of higher dimensional spaces, from the combinatorial properties of spin networks, or from the symmetries of abstract algebraic structures that predated spacetime itself. Some frameworks suggested that the speed limit might arise from the maximum rate at which information could propagate through an underlying quantum computation, as though the universe were a vast, evolving algorithm whose rules mandated a finite communication rate. Others framed it as a manifestation of the deepest symmetry in nature, Lorentz invariance, without which causality would unravel and the logical structure of physical law would dissolve. But in all such explorations, the speed of light remained a pivot around which every workable theory turned, a boundary that persisted even when space-time was treated not as a continuous expanse, but as a pattern of relations and interactions at the Planck scale. And while this theoretical work unfolded, astronomers continued to push observational frontiers. They captured light from galaxies born when the universe was less than 1 billion years old. Their ancient rays stretched into infrared wavelengths by billions of years of cosmic expansion. They studied quasars blazing at the edge of the observable universe, their beams of ionizing radiation carving out transparent bubbles in the intergalactic medium. They traced the flickering of distant gamma-ray bursts, timing the arrival of photons across a spectrum of energies to test whether even the most minuscule deviations might emerge at the threshold of quantum gravity. But despite every attempt to reveal cracks in the constancy of light's speed, the universe responded with unwavering consistency, as though determined to preserve the integrity of its most fundamental boundary. Meanwhile, closer to Earth, the speed of light shaped technologies that threaded through everyday life. Fiber optic networks carrying pulses of infrared light across oceans and continents brought entire nations into instant communication, only limited by the milliseconds required for photons to travel through glass. Interplanetary communication arrays monitored distant probes, calculating round-trip light delays to choreograph operations or correct trajectories. Even the architecture of global commerce depended on the finite speed of light. Financial markets, satellite networks, and secure communication systems all factored relativistic propagation delays into their timing algorithms. The speed limit, discovered in the motions of Jupiter's moons and refined in the equations of Maxwell and Einstein, thus governed the rhythm of modern civilization, becoming as practical as it was profound. As research at the interface of quantum information and gravitational theory advanced, new insights emerged suggesting that the speed of light was not only a limit for motion, but a deeper boundary on computational complexity. Systems attempting to scramble information, like black holes, which are among the fastest information scramblers in nature, processed quantum states at rates constrained by causality, with the speed of light defining how quickly information could mix, propagate, and entangle across a region of spacetime. These discoveries linked the study of black holes to quantum chaos, thermodynamics, and condensed matter physics, revealing unexpected correspondences between seemingly unrelated fields. Again, the speed of light appeared not simply as a parameter in an equation, but as a universal bookkeeping rule, regulating how fast the universe itself could compute. Even as new observational windows opened, neutrino astronomy, high-energy cosmic ray detection, and the study of fast radio bursts, the narrative returned repeatedly to the same anchor. Neutrinos arriving from distant supernovae raced neck and neck with photons, confirming that even these ghostly particles, capable of passing through light years of solid matter, adhered to speeds fractionally below light's. Ultra-high energy cosmic rays, striking Earth's atmosphere with energies millions of times greater than those produced in terrestrial accelerators, still bowed to the speed limit, their interactions governed by relativistic kinematics. Fast radio bursts, bright as galaxies for milliseconds, offered new tests of dispersion across intergalactic media. Again and again, the universe demonstrated consistency across extremes, as though every phenomenon, no matter how exotic, had signed the same cosmic pact. And so, as physicists and astronomers, philosophers and engineers, historians and dreamers surveyed the unfolding tapestry of the cosmos, they found themselves returning to a constant that connected ancient stargazers to the edge of the observable universe, that linked the behavior of electrons in graphene to the evaporation of black holes, that shaped the first microseconds after the Big Bang and the daily functioning of satellites above a turning Earth. The speed of light stood not as an arbitrary limit, but as the quiet scaffolding behind every law of physics, every thread of causality, every exchange of information, every observation made by any creature capable of looking outward and wondering what lay beyond.